And here is Austin. Hello, Austin.
Hey,
Everybody, Austin Sendek is from Stanford University. He's a professor of material science and engineering, and he will be talking about machine learning. So, combining two very hot topics and leading us through machine learning in the solid state battery material discovery. Austin, please go ahead.
all right. Thanks, Heiko, and thanks to Christoph and the whole TechBlick team for the opportunity to speak with you today. Um, that was a great talk by Kevin because he touched on several things that I was going to mention, including sulfide solid electrolytes and also non-automotive silicon anodes. So happy to share that I have a Whoop 4.0 on my wrist, which is one of the first commercialized silicon anodes out in the world. So thanks to Kevin for that great talk. As Heiko said, I'm here to talk about machine learning in battery development. And given the solid state focus of this session, I figured I would talk about our work specifically on solid state electrolyte development. Um, I'm also actually my day job, so to speak, is as one of the co-founders of a company called Aionics, which is focusing on computational battery design using some of the methods I'll talk about today. So I'm going to wear my Stanford hat today, but if there's any questions or anything about Aionics, I'm happy to get into that as well. So, first of all, why do we care about this world of machine learning and AI? Well, computing power and AI are improving really rapidly, and this was maybe a harder pitch to make before ChatGPT came out, but of course now everyone is well aware of this. And there's really two kind of dual exponentials or dual revolutions here. One is just the exponential increase in computing power, which is Moore's law, of course, and then there's also machine learning, which scales typically like a power law with the amount of data. And so you have computers getting faster and faster. You have models getting better and better. And so you can ask yourself the question, well, what happens when these collide and computing becomes essentially infinitely cheap or basically free, and machine learning models become infinitely accurate? Um, what does that mean for us? We're careening towards that future. What does that mean for us here in the world of battery development and material science? Um, what we're seeing, and I guess this is my observation now as Aionics, but what we're seeing, I think, in the workforce is essentially a bifurcation of tasks between those well suited to humans and those well suited to computers, right? So the human scientist on one side is really excels with creative problem solving, but is not built for rote computation, right? Not built to just jam through huge numbers of calculations or to run, quantum mechanical thought experiments in your head. But the creative problem solving element is certainly what humans excel with. Humans are online about 40 hours a week, and they cost roughly $10,000 per month to first order. The computer, meanwhile, is really bad at creative problem solving, but excels in rote computation. It's online every hour of the day, and it's going to cost roughly 100, essentially the same cost as the human for about 100 CPUs per month. So about $100 per CPU month. So the question is basically, how do we sort of bifurcate the tasks to this bifurcated workforce, and what does this mean again for the world of solid state battery design? Well, I would say we don't have to worry about losing our jobs anytime soon. Empirically, we know from many different applications, but my favorite is Gary Kasparov's centaur chess observation that the best way to achieve an objective is to pair a creative human with a good computer, right? And as we saw in the case of Deep Blue and the chess playing robots, the best chess performer is the performer that pairs a good human brain with a good computer, and that can beat a great computer in isolation, and that can beat a great human in isolation. So the both of these pieces are really necessary in this future. So with this in mind, how has the solid state game changed over time? So a couple points. So high performance computing and machine learning have enabled the following. One is models for predicting historically difficult to predict properties. Second is high throughput screening of all known solid state compounds. Third is prediction of commercially relevant properties like synthetic accessibility and cost, which, like